Today I'm going to discuss matrix representation of L square, L square, LZ, L plus, L minus, S square, SZ, S plus, S minus, SX, SY. Here also LX, LY also. Okay, we are going to write the matrix representation of angular momentum component and spin component, spin angular momentum components in terms of matrix form. So we know already eigenvalue of L square is h cross uh, L square eigenvalues h cross L into L plus 1, right? So eigenvalue of LZ operator M h cross. Okay, eigenvalue of L plus h cross root of L minus M into L plus M plus 1. L minus eigenvalues h cross root of L minus M into L minus M plus 1. Okay. In the similar way, S square also h cross square M into M plus 1. Okay. Sz is equal to Ms. This is actually Ml. Okay. Orbital angular momentum. This is spin orbital magnetic momentum. H cross. And L plus L minus also same. So first I'm going to discuss with L square. For example, L square here I am going to apply on L M state. Okay, then I can get H cross square L into L plus 1 into ket vector. So I'm going to, this is equation number 1, multiply this equation by bra vector, which means L prime M prime. Then we can write this equation like this: L prime M equation number 1, okay, into L square L minus, sorry, L comma M equal to H cross square L into L plus 1 into L prime M prime L comma M. So now we can easy. This is ket vector, we can represent it in column vector. This is bra vector, we can represent it row vectors. For example, here I am taking L is equal to 1. L equal to 1. What are the M values? M is equal to 1, 0, minus 1. Then you can write the combination. the matrix representation of this equation. So this term we can write like this, right? So we already know how to write this type of equation in terms of canonical delta functions. Then we can represent these terms into the matrix forms. The h cross square L into L plus 1. This one is delta L L prime. Sorry, canonical delta M M prime. So we know how to check these values. We already did 2, 3 classes. So if you don't know how to check this value, then go and watch angular momentum, the matrix representation of angular momentum. So that is no problem. So if you can't watch that videos, I can explain here. First, you need to check this canonical delta. If it is going to normalize, which means 1, then you can check this one. Okay, this also exists normalized condition. Then you can apply the what are the L values, M values. Then you can get the eigen values in terms of matrix representation. We know that these ket vectors are represented in column vectors. These bra vectors are represented in row vectors, right? So like that, I am going to write here. So listen carefully. L square, L square. Wait. Okay, good. So these are the combinations I can write here, right? So L one one. This is M, right? So therefore, I'm going to write these combinations like this. This is 1 1. Next 1 0. We know how to calculate this. How many rows are formed? How many columns are formed? And formula is there, right? So you need to follow that formula. 1 minus 1. So therefore, I'm going to write these things here. 1 and 1. 1 0 and comma minus 1. Here also same. What is that mean here? These are the ket vectors, bra vectors. Here, this is 1 comma 1. Okay, these are 1 comma 0, 1 comma minus 1. Okay, this is ket vectors. These are the bra vectors. Ket vectors are represented by column vectors. Then we can multiply these things. So if you multiply these things, see, I'm going to explain first thing, which means uh, this bra vector and this ket vector. So check here, please observe carefully. So all are similar passes, there is no changes. L square 1 comma 1 equal to h cross square. So this is 2. Okay, 1 plus 1. The remaining thing, this one, both are same, right? This one is 1, this one is 1, 1, 1, which means this one is goes to 1, this one is goes to 1. So we already know the Dirac delta function. We can check like this. So maybe you are all aware of this. 1 if I equal to j, right? 0 if I not equal to j. Then only we can substitute. This is j and j prime. Carefully here. J and j prime. This is m and m prime. Then you can use here only L values, not M values, because this scalar eigenvalues are there in terms of L values. This is why I'm using 1 here, 1 here. Then I can get 2h cross. I'm going to write this thing here. Okay, h cross square. See, I'm going to multiply this bra vector and this cut vector. Different states, right? Then it is becomes to 0. This state and this state, this becomes to the 0. Right? In the similar way, I'm going to multiply all these things like this. Okay, so this one different state, then I can 0. Then we can apply only this state. So here L prime, L are same, then M is 0. Then we can get here 2h cross square. This one is 0 because of different states. Here this bra vector and this ket vector, different states, right? 0. This bra vector and this ket vector, different states, 0. These are the two same states, right? Then we can get this L, this is M, right? This is L prime and M prime, L prime and M prime. So therefore here also we can get 2h cross, 2h cross square. This is how this L square are very simple compared to J square. Then again I'm going to discuss LZ, LZ. In case if you apply LZ on this state, L comma M, so what are the eigenvalues of LZ? MH cross, right? Then you can write MH cross. Then you can mention here, this is L orbital spin magnetic moment. Sorry, orbital angular momentum in terms of orbital. Okay, this is spin number. So this spin is generated by the orbital rotation of electrons. Okay, then you can multiply the same thing, similar formulas. L prime and M prime if I apply the, so these are the way. No need to by heart these things because in CSR you can derive within the 1 or 2 minutes whatever the matrix are there we can derive easily. So don't by heart these things, then you can solve like this. Okay, so this is ML H cross and L prime M prime. This is L and J. Sorry, L and M. L prime M prime. L Z L prime M. So you need to find this formula first. Then you can. This is J. This sorry. This is L. This is L prime. Delta. This is M. This is M prime. Okay. This is the final formula. Then we can check. Remember each and every time I told you one key point here. First, again I'm going to say here. First, we need to check this factor. If it is goes to normalization, which means 1, here the L is equal to 1, same state is there 1 1, then we can get this Dirac delta Kronecker delta function is 1. Then only you can check this function. Okay, this is also goes to the normalization condition. In case if you get this one 1, okay, same state, then you can get the Kronecker delta function is 1, right? Then you can apply what are the ML values. Okay, ML values here. Carefully here. We need to apply here the M values, not L values. Okay. Okay. So L square here I'm going to arrive the again box. Okay, this is enough for me. Uh, Here I'm going to write LZ. So what are the L values and M values? L values, L equal to 1, right? M equal to 1, 0, minus 1. Quantization rules. Then you can write the same things here. This is 1, 1. This is 1, 0. This is 1 minus 1. Same thing here also. Raw vectors 1, 0 and 1 minus 1. So you know, right? This one is you are aware of these things already. What is this cat means? This is L, this is M, this is L prime, this is M prime. So now you can multiply carefully. This is same state, right? Then you can get here the answer. First I'm going to check this one. So here the L equal to 1, M equal to 1, right? And M equal to 1, L equal to L, sorry, L prime equal to 1, right? M prime is 1. Then here M 1, M prime also 1. These two are normalized condition. Then I am going to apply, many students are going to apply this here. I observed in examination papers, many students are apply this. This is not correct here. This is spin orbital angular momentum. Okay. Two type of electron motions are there. One is electron is rotating around itself, another one is electron rotating around the nucleus. So electron itself rotating around itself, that is spin, right? That is where generally denoted by the spin S. Okay, and electron is moving around the nucleus, that is the orbital angular momentum. Okay, so that is L. Here the spin, this one, M equal to 1. Then you can say M equal to 1, what you get here? 1 H cross. Okay, 1 H cross. Next, same thing here. I multiply this thing and this thing. I get here 1 H cross. These are different states 0. These are different states 0. And this one is different state. This is same state. Now guess what is the eigenvalue here? Okay, L prime or say this is 1, this is 0, this one 0 0. Then what is value here? 0. Here the answer is 0. Careful. Okay, this is answer is 0. Then this one is 0. Next 0 0. See here, this is minus 1, right? Then you can get here minus 1 H cross. This is the uh, LZ matrix representation. Now uh, we can try another thing. L L plus. So same formula L M I am applying. So you know, right, why I am wasting time? L prime M prime. Then I can get the what is the H cross root of L minus M into L plus M minus 1. Then, so because, sorry, I'm going to explain this thing. Just wait, just wait. Okay, no need to hurry. So this is a quantum state. I'm going to apply L plus operator. In case if you apply L plus operator, it will not affect on the this L. Okay, it will not affect. Only it show the effect on this M state. You know the what is the reason why it is not affect L? There's please try to comment below. Then I can reply the what is the correct reason. Okay, please remember this one. Uh, L plus if you apply this quantum state, it increased by m state by 1 unit. So which is why I'm going to write here this state con different state m plus 1 because it increased by h cross unit, which means one state, unit one state it is increasing. So then what are the eigenvalues here? Root of L in, sorry, mm, L minus m into L plus m plus 1. Okay, so then you can apply the L prime m prime L plus m L again same method, same formula, same technique you follow, then you can get this formula. Okay, delta, this is m. Okay, remember j into j prime delta m into m plus 1 here. Okay, m prime m plus 1, m prime m plus 1. This is the formula. So by using this formula we are going to write matrix representation of L plus. Whenever you want to is a eigenvalues, you need to know how to derive this matrix representation. Then you can easily remember this. What are the this matrix representation values at a different state? J is equal to 1, j is equal to half, j is equal to 0, j is equal to 3 by 2. So I observed in many national exams they are asking different type of states. Then what are the matrix form of these operators? Okay. So here, okay, this is L plus, right? I'm going to derive this one is quickly. Sorry. Mm. Okay. Here you can take the L plus, and here 1 comma 1, 1 comma 0, 1 comma minus 1. Here 1 comma 1, here 1 comma 0, here 1 comma minus 1. Then you try to multiply these vectors. I mean, uh, get vectors. Then you can get the answer. Then you can get answer easily. Don't worry. So here we are going to multiply one by one. Then you can get the final answer. Okay. Now it is right. So this is the same state, right? This is same state, but but here the formula is different. You need to check each and every value. So j is equal to 1, j prime is equal to 1, but here if you put m is equal to 1, you can get here 2 1 state. This is in case if you multiply this one and this one, here you can get it. This is 1, this is 2. Okay, 2 1 state, right? This is 0. So that then entire equation becomes to the 0. Second thing, if you multiply this one and this one, okay, this one and this one, if the 0 is there, so then you can get 1 1 state. Then entire equation becomes to be some value. So what is m value? What is, this is not j, this is l. So L equal to 1, M equal to this M value. M equal to 0, right? Carefully here. So M is equal to 0, which is why this one is 1, this one is 1, and this one is 0. And remaining thing is, so 1 plus 1, 2 root 2 into h cross root 2. This one is 0. Okay. So like that, you can multiply all these things, then you can get this answer. This one is root h cross, correct? 0 and 0 and 0. This therefore the L plus operators, the L plus operators are the, so 0 h cross root 2, 0 0 0 h cross root 2. So 0 0 0. Okay. Next thing, L plus is 4. Now I'm going to derive L minus. So if you apply L minus on this quantum state, it is decreased by one state here. So then I can get eigenvalues. First I'm going to L m minus 1. So root of minus, right? L minus m into L minus m plus 1. Okay. Then you can get the answer, the final formula like this. L minus, if you apply root of L minus m into L minus m plus 1. This one is delta I, okay, I mean L prime, delta m prime, okay, m minus 1. M minus 1, this is the final formula that we want. Okay, then you can check the matrix formation. So I'm going to write here the final answer. So you need to check this one because its time is going to increase. The L minus, right? L minus. In case if you can't get answer, just please try to comment below. I can reply your comment. Or else I can send my notebooks to. Okay. One, one, 1 comma 0, 1 comma minus 1. Here also 1 comma 1. Okay, 1 comma 0, 1 comma minus 1. So the quite opposite we can get answer here. So exactly here the h cross root 2, 0 0 0 h cross root 2 0. This is the answer. Therefore the L minus operator is 3 by 3 matrix 0 0 0. Okay, root 2 h cross, or h cross is outside the root. This one is 0 0 h cross root 2. Okay, so it's better to write h cross the in front of root. Okay, now I want to know the what is a Lx and L plus matrix. Okay, so we know the Lx, you can get L plus L minus divided by 2. This is the formula. Then you can add it. In case if you try to add this thing, then you can get this final answer. The two equations are there. You need to follow that two matrices, mean 3 by 3 matrices. Then you can get the answer this thing easily. 0, 1, 0. Next, Ly. If you want Ly, this is the formula. L plus minus L minus divided by 2I. So therefore, the h cross divided by root 2, h cross divided by root 2, so 0 minus I 0, okay, I 0, I 0, I 0. So these are the L square, Lz, L plus, L minus, Lx, Ly matrix representation in terms of L is equal to 1. Okay, next. So you need to try the Sx and S square. It is slightly different. I'm going to explain one thing, remaining I'm going to in terms of exercise thing, right? So S square is applying on the state. For example, please be careful here. If you try to apply the S square, this is S, okay, comma, this is M, S. This is the quantum state. Okay, if you apply this quantum state, then you can get h cross square S into S plus S comma ms. Then you know this. What is the um, equation? Then you can try to write here S prime and m1. This is m. Okay, this is S. So similarly, I'm going to here the S prime, m prime, S square, S m equal to h cross square S into S plus 1. This one is delta S prime delta m prime. So I'm going to here you need to careful. So what is S value? What is S value? Here I'm taking S is equal to 1 divided by. Then what is ms value? Ms spin angular momentum plus or minus 1. This plus 1 divided by 2. This minus 1 divided by 2. So there is no 0 in between, plus 1 divided by 2 minus 1 by 2. Be careful here. How many quantities are coming here? How many rows are coming here? How many columns are coming here? 1, 2. Okay, only 2, right? Then I'm going to use the two vectors like this. This is S square. So S 1 divided by 2, 1 divided by 2, 1 divided by 2 minus 1. Only simple, right? 1 divided by 2. Second thing, 1 divided by 2, 1 divided by 2 minus 1 divided by 2. Okay. So if you multiply the other thing, the same thing also here, right? Then you can get here the 0. This is different state. This is different state. This is 0 and then this is 3 divided by 4 h cross square. So therefore S square matrix is 3 divided by 4 h cross square. These are very very important. I'm going to explain this each and every time because are the Pauli's matrices, 2 by 2 matrices. Next, SZ. If you apply SZ, then only you can get free matrix SZ component. So SZ we know, right? SZ. If you apply SZ on this quantum state, this is the quantum state S and MS. Okay, MH cross MH cross S into M S into M. Then then try to write this thing like this: S prime, M prime, S Z, S Z, S and M equal to M H cross. This is S prime, M prime, S, M prime. Okay, so therefore this one S prime, M prime. Similar procedure, right? Delta S and S prime, delta M and M prime. Okay, very good. So if you try to write the matrix form here, so matrix form I'm going to write here. This is SZ, SZ. So quantum set 1 divided by 2, 1 divided by 2, and 1 divided by 2 minus 1 divided by 2. Okay, so then brass state 1 divided by 2, 1 divided by 2. This is 1 divided by 2 minus 1 divided by 2. So if you try to multiply this thing, then you can get here h cross divided by 2, here 0, here the 0, this one minus h cross divided by 2. Therefore, sz is equal to h cross divided by 2, 1, 0, 0, minus 1. You know this one? Did you remember this thing? This is Pauli's matrix Z component. Okay. So sz 1 divided by, sorry, h cross divided by 2. This is sigma x. Sigma x. So Pauli matrix also there. In case non-relative, see, this is the non-relative quantum. Sorry, if you try to explain in relativistic quantum mechanics, uh, maybe you can observe in relativistic quantum mechanics Dirac matrices, not Pauli matrices. Pauli matrices are 2 by 2 matrices. Dirac matrices are 4 by 4 matrices. Okay, these matrices are exhibit some unique properties. Then you can understand that unique properties. Then try to remember that properties. You can know you can recognize the what is the importance of this Pauli matrices. Okay. So in the similar way, if you try to explain the S plus. So here I'm going to directly. So you already know the formulas. Okay. So 1 divided by 2, 1 divided by 2. This is 1 divided by 2 minus 1 divided by 2. And this is 1 divided by 2, 1 divided by 2. This is 1 divided by 2 minus 1 divided by 2. S plus, right? This is 0. H cross 0, 0. So therefore, here I got H cross S plus. S plus is equal to 0, 1, 0, 0. So remember this one. If you want to know the what is Sx and Sy, then you need to know the what is S plus first. And similarly, S minus equal to 1 divided by 2, 1 divided by 2, and 1 divided by 2 minus 1 divided by 2. And here the 1 divided by 2, 1 divided by 2, 1 divided by 2 minus 1 divided by 2. So this one is 0, this one is 0. We can get this one is H cross 0. So therefore, S minus equal to H cross 0, 0, 1, 0. So therefore, if you want to know Sx, what is the formula of Sx? S plus S minus divided by 2. So therefore here, so if you try to add Sx and S plus and S minus, then you can get the Sx divided by 2. Therefore here, like, you add, you can get this one. By 2 is the 0, 1, 1, 0. So therefore this is S, x is equal to h cross divided by 2 sigma x. This is Pauli's x component. Okay. Then S y equal to S plus minus S minus divided by 2i equal to, so h cross divided by 2 to 0 minus I 0. So therefore Sy equal to h cross divided by sigma y. These are the Pauli matrices, right? Sx and Sy and Sz, these are all Pauli matrices. So this is all about the matrix representation of L square and Lz. So if you try to remember what we discussed in above, first we discussed L square. Lz, L plus, L minus, Lx, Ly. Okay, then S square, Sz, S plus, S minus, Sx, Sy. So these are the components we derived in terms of matrix form. So in case if you get any doubt in this topic, then you try to comment below, then I will reply.